But one wintry night in particular, we stayed a little late at my grandparents' house. And when we got back to the house, the whole gaggle kind of marched in. I was second from the bottom. Katie kind of crawled in. I was right behind her. And I parked myself there, unbeknownst to my parents. And after a little while of searching for me inside, high and low, they can't find me. They finally go outside, and there I am, like this, in the yard, just staring up. Because for the very first time in my life, I had seen the stars. I would note this was an image. This is a real image. This is Photoshopped to some degree, but everything you see here is actual. It's a time-lapse photo that a student of mine took last year up when I was teaching in Vermont. The skies up there are a little bit clearer than they are here in Florida. Just a hint. But I just fell in love with this, and as I tended to do, I instantaneously bombarded my parents with so many questions. What are those? Stars. What's a star? I always feel like Pumbaa when I say this. It's a big burning ball of gas, billions and billions of miles away. I said, so how far is that? And they're like, really far. How far? And they, well, sun's a star, and that's pretty close. Like, what? Sun is a star? Sun is one of those? And my parents are like, yeah. I said, oh, okay. And so it took me a little while to wrap my head around this. I was 5. But I eventually got there. And I said to them, so let me get this straight. Sun is a star, and we live here. And they go, uh-huh. I go, and all those are stars, so they're suns like ours. And they went, uh-huh. I went, so are there people out there? And I had finally reached that breaking point where my parents were like, just go to bed. And that was somewhat typical of my parents to a fair degree. I was fortunate. My mother was a mathematician, so I got a lot of my answers as I was growing up. But it would take me a while to kind of learn these things through and through. I would share with you, oopsie, gimme. There we go. Another picture, also from last year. Again, slightly clearer skies. So I keep growing up, and I want to know about these stars. And the biggest problem I have when I'm talking to people about astronomy is that you have no idea of the scale of which I'm talking about. If I say, what's a foot, you guys kind of go, if I say yard, The second you ask a human being what a mile is, it starts getting a little trickier. So, run 6 or 7 or 8 minutes, and okay, you're going to be in the ballpark of a mile, maybe plus or minus 10%. I say to you, how big's the planet? Okay, now you're screwed. So it's about 12,000 kilometers across. But we need to do slightly better than that. So let me pull back up this, and let's see how big stars actually are. If I can do this. You end. You die. And you begin. So our planet is, like I said, about 12,000 kilometers across. And if we look at all the other rocky-type planets, we win. But that's nothing, because we have to look out to the Jovian planets. And now Jupiter's about 10 times bigger than we are. That's small. Sun's about 10 times bigger than that. So it's 100 times larger than our planet. But that's a dwarf star. And it's really, really well named. Because if we start going out and looking at some of the larger stars, at this point, we see Arcturus, Pollux, and Sirius 2.5 times larger, 8 times larger, and 25 times larger than our own star. If you've got really good eyesight, although not on this monitor, Earth is about the size of a pixel at this point. But we're going to blow by. Oh, I've skipped something somehow. Impressive. That happens. No, we're good. Good. I've got 2 things going on my screen. So if we go out farther and farther and farther, yeah, they get bigger. So all of a sudden, we have 4 of the slightly giant stars, as we say. And these aren't the largest. They're some of the closest largest. Those stars that you saw, the largest of them was about 1,200 times larger than our star. So that is literally 100,000 times larger than our planet here. So as I try and always convey to astronomy students, you are a tiny, infinitesimal, little, unimportant speck in the universe. And it's important for students to truly understand that. But the scales are really hard to work with. So ultimately, we need to kind of break things down into a metric that you're going to be more familiar with. So to do that, let's start shrinking things. If I take everything to be like a 1/10 billionth scale, everything's going to be 10 billion times smaller than it is right now. You're roughly the size of an atom. I can't show that to you. It's so small. But at this scale, if I wanted to go to the nearest star, that's a drive across the continental United States. That's the closest star to us. It's 4 and change light years away. So this scale is, again, not going to do it. We need to go to 1/quintillionth of the scale if we're really going to start getting this. That means 1 times 10 to the negative 18. It's a lot of zeros. At this point, you're about the size of an electron. And if we really want to kind of figure out the size of things, the Milky Way, that which you're looking at here, and let me go back over here, gimme, maybe, today, if possible. Nope, too far. Back up. There we go. Hey, it's our universe. It's our galaxy, excuse me. This is about the size of a football field at 1/quintillionth scale. And just in case we were curious, it's a big image. You're there. Hi. It's kind of small. At this point, the observable universe, that's not the whole universe. The observable universe, which is much smaller than the actual universe, is the size of our sun. So you should be kind of getting an idea that it's a big place with lots and lots and lots of stuff. So we're basically swimming in this ocean of space that is filled with little grains of salt that, in this analogy, are basically stars. So we need to kind of keep going and understand the scale a little better. So let's go back to my youth for a little bit. And now we can talk, hopefully, about something else. So, I should tell you, let's look at the universe for a second. Why not just describe it? I can also show it to you. So this is from the Sloan Digital Sky Survey. This is the 4th data release. This is actually several years back. This contains about 500,000 galaxies and 75,000 quasars. My research is focused on quasars. Each thing you're seeing here is real. This is not an animation. These are actual galaxies. Your galaxy is centered in the middle. It's already long, long gone. This is what the universe looks like. We've gone out, we've hunted around, and we've tried to map out our sky. And we've done like half of a percent. And that's what you're currently seeing. Space, as you pull back to what I oftentimes refer to my students as the God perspective, starts to look nothing like you thought it did. As you go back farther and farther and farther, these galaxies are retreating from you. Space is also getting bigger, mind you, and faster than the speed of light. So it's not only a big place, it's getting bigger. And because of that, everything starts turning red out at the outskirts. And so in a second, we're going to get to the point where you get to see kind of what we've mapped. And it's a pathetically small amount of space, and we're only seeing the really bright things. There's lots and lots which we haven't currently seen. And that's what's seen here. Where the gaps are things like sun. It's hard to see galaxies when you're looking through a star. But these are the galaxies that we know about. It gets bigger. So as we start to go back farther and farther, these aren't galaxies. This is the primordial fireball from whence you came. This is the beginning of time, as far back as we can see it, back to about roughly 500,000 years after the beginning of time. A lot actually happened between then and that 500,000. In case you're wondering, the universe is about 14 billion years old. And you can notice this structure, by the way, because if you turn on your radio and you hear static, some of that static is leftover energy from 14 billion years ago. It's still ringing from that little explosion, if we want to call it that. So going back to my own past, I was hooked on this stuff. And growing up, it was hard to get me to stand still. If any of you have seen me in class, you know, even with a broken ankle, I'm all over the place. And so we were a little poor. We didn't have a lot of money. And so the station on TV we watched was pretty much PBS, because that was the free one. And one day I met Carl Sagan and Cosmos. And my parents loved this because for an hour a week I would sit still. And that was awesome for them. 7 to go, 1 is parked. Good. And I didn't know this at the time, but I would make mention of it because I already have. Let me grab my little laser. This thing here is a quasar. Sagan didn't actually know what he was talking about with this at the time. No one did. It's not his fault. And that's what my research is to this day. I certainly didn't know it at the time. But Carl was going to teach me a lot. Now, Carl, of course, seen here, the infinite billions and billions of stars in the universe. I had to grab this cover because this really puts him in a good light in the sense of he was the showman of science. Today that title probably goes to Neil deGrasse Tyson. You guys have probably seen him doing specials and other things. I've met him. He's a really great guy, and he is also a great communicator of science. And that's a difficult thing to do. And he had this ability to really take incredibly complex ideas and parse them such that even the layperson could completely understand them. And yeah, he taught me a lot. The first thing he taught me was that at the beginning of the universe, there weren't things like carbon and oxygen and nitrogen, things that you kind of need a lot. Because without these things, I can't make a human being. I really only had hydrogen, a little bit of helium, a little bit of beryllium, and a little bit of lithium, and nothing else. And it took a long time, 380,000 years, for that to form. And he tells us that within the furnaces driving these stars is an engine that is going to create these heavier elements for us that we're ultimately going to be made up of. So in this sense, he liked to say to us, we are children of the stars. Yeah, that only helped me dive deeper into this hole. I was like, oh my God, I come from a star. That's awesome. So he goes on, and he starts teaching me about SETI, or the search for extraterrestrial intelligence. And I get to learn fun little stories, like back at the beginning of the 20th century, in the 1920s, there was this great fascination with Mars. All these stories were coming out, aliens on Mars, and these Martians are going to invade, and you have all the H.G. Wells stories, and Percival Lowell is going nuts trying to find people on Mars. He's misinterpreting Italians because he can't speak anything other than English, and takes the word channel and turns it into canal, and says, ah! The Martian people are dying, and they're making these big canals to move water from the poles to their great cities underground. Woo! Went off a little into left field, but the US military in the 1920s started sending radio signals to Mars, going, we might want to meet these people in case this is true. Unfortunately, we wouldn't know for decades to come, but in the 60s, we got our first good pictures of Mars. It's dead, for the most part. I'll talk a little bit about Mars later on, but as far as we're concerned, at this point, we have certainly found no life on Mars. I'll argue against that a little later on. But SETI kind of cropped up in the meantime, and we've been listening for a long, long time. We've sent a few messages using radio waves, but for the most part, we listen. Carl was not one of those guys who's going to sit around and wait for you to contact him. He was going to reach out and touch someone. So here's Carl with his first attempt to reach out and touch someone. Two of the craft that we sent out in the 70s, Pioneer 10 and Pioneer 11, Carl basically pissed and moaned until he got his way. He was good at this. And he attached postcards to these two craft that we were going to send out into the stars. They're going to do a brief little cruise to the solar system, but their primary objective was to go way out there. They haven't left the solar system yet, 40 years later. It's a big universe again. But what a beautiful message, if I can get to it. Which is huge. Come down. One more. Thank you. So what an amazingly simple message it was, because think of the challenge. You have to communicate with an alien species that doesn't speak any terrestrial language simply because they're not from here. So you have to tell them a lot of information. First piece of information, this is us. Over there on the right, man and woman. And standing behind, or parked behind them, is the spacecraft you can see here. This was Pioneer 11 or 10. And the idea is, here we are humans, this thing behind us, we made this. This is ours. We did this. And then he left you a roadmap. He said, all right, here's our solar system. 8 planets, you don't count. And we kind of shot this thing off. But that's not a really good roadmap. That's like saying, OK, to get to my house, you need to know how to get to my block. And then you can go down the street. I'm like the 6th house down. That's not going to do it. So we put in this big roadmap here. And the roadmap is really simple. In the 50s and 60s, we found these beacons in space that were pulsing out at incredibly regular intervals. More accurate than the wristwatch you have on, more accurate than the clocks on your cell phones, more accurate than the clocks on your computers. And at first we said, oh my gosh, these are intergalactic signposts. You know, eat at Moe's, or don't come here, giant black hole. It took us just a little while to say maybe that's a little fantastic. And we can do a little better than that. It turns out that they're called pulsars. They're these rapidly spinning stars that pulse extremely accurately over incredibly long periods of time. And so what beautiful signposts. And so we said, here are 14 of them, where we know their positions and we know their timing. 14 is an odd number. Well, we chose 14 because what if you live over here and you've never seen the ones over here for whatever reason? There's still a bunch that are close to you that you will have seen. And you only need a few to figure out, aha, there they are. Also over here next to the woman, this is considered the center of our galaxy. So it gives you a relative distance from the center of the galaxy to where we are, with a lot of signposts going there. And then a road map here. The only problem is they don't speak any language that we're using. So we use quantum physics, because why not? This is a diagram that any spacefaring race that would be capable of finding and getting this message would understand. The physicists in the room will probably get this. The lay people, you don't need to. It's called the hyperfine splitting of a hydrogen atom. It's a very, 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 very basic piece of physics. But from it, we can get a timing. And from that, we can get a distance. Aha. I can tell you the timing of the pulsars. I can tell you how far away they are. I can also tell you the height of a human being. I can tell you the sizes and distances of the planets. So we figured out this way to say, here we are, this is how you find us, here's the language we're going to speak to you, and it's of course math, because math is math is math, no matter where you go. It's always going to be the same. I would note that, as something I always find humorous, there was a big conniption put out over the fact that nudity was sent out into space, as if this was intergalactic porn. It didn't go very well with some certain high-up people who control budgets. And so on our next effort, Carl said, I'm not going to send them a postcard. I'm going to send them an LP. I hope they're into slightly passé technology, but you'll notice the naked people have gone. It's a shame. It's nice to say, this is us. Anyways, we sent them a record. And it's made of solid gold, so they might want to keep it. But it basically says, all right, this is a turntable. We gave them one. This is a needle. We gave them several. And these are all instructions how to use it. You see the same, here's our language, here's our position. We tell you here is basically how to play the music. We send lots and lots of music. Elvis is on there. What's the Men in Black line? Elvis isn't dead, he just went home. And there's a lot of video on there as well. And we tell them this is the screen rate you want to go at, 32 frames per second. And the first image you should get is a pristine circle. Pick something simple, the most basic geometric shape you can think of. And these went out on two spacecraft called Voyager 1 and 2. Voyager 1 is currently the most distant object we have sent into space. It's still in the solar system. It's a big universe. So we've been making these efforts for a while, but we haven't really found anyone, of course. You would have known by now. And so we need to start being a little more intelligent. And so in the 1960s, a guy named Frank Drake came along, and he came up with this infamous and constantly abused equation. Now, the preface for this. This is not science. This is what in science we call an Ansatz. It's a nice German word. And it basically means really, really well-educated guess. Guess. I have to emphasize that. And the idea was to say, well, since they haven't come to us, how can we try and estimate how many civilizations there are in space? And Frank Drake sat around for a while, and he goes, OK, this is how we're going to do it. He goes, all right, n civilizations. The number of civilizations in space are equal to these 7 ideas multiplied by each other. So n star. Well, that one's easy. The number of stars in the galaxy, 400 billion. That was easy. You can find it pretty easily. You look at a representative piece of sky, and then you basically circle it around the galaxy, and you go, aha, I know how many stars we have. But there's a slight complication. As we saw earlier on, there are a bunch of different kinds of stars. Some of them are not so friendly to people. Fortunately, of these 7 types, 3 of them are probably friendly to life, and they make up 97% of the stars in the sky. So we got that going for us, which is nice. 2 of those other stars are shaky. But if we add those in, and I'm serious about that, it means that of all the stars in the sky, 99.989%, so all of them, are habitable for life. Only a tiny 0.011% of them are the giant stars that will cook you. Basically, they put out tremendous amounts of radiation, not so good for people, perhaps good for popcorn. There's another complication, though. If you're too close to the center of that galaxy, our galaxy, there are too many stars there, and they are also going to cook you. Not good. If you go out to the edge of the galaxy, there aren't enough of the heavy elements that, again, make up you and I. We can't make a person out there. We can't make life out there. We don't have the raw ingredients. This limits us to 10% of the stars in the sky. So we're down to 4 billion stars. All right, not bad. Now, F sub p up there is the fraction of those star systems where we expect there to be planets. Now, back when I was raised, we had 9 planets. Pluto got the proverbial boot. It deserves it. It's not a planet. Bye. So we have 8, and we have slight applause. And as I was growing up, there were 8 planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and nothing else. In the 1980s and 1990s, and for the first time in 1995, we found another planet. It was enormous. It was about 4 times the size of Jupiter. It is not somewhere you're going to have someone live. But as time has gone on, we've found a tremendous number of planets. And I'll tell you more about that later on. But we'll say conservatively that half of the stars in the sky have planets orbiting them. Not bad. N sub e, the number of those planets per system that should be somewhat hospitable to life. Now, here in our solar system, we, of course, have Earth. We are the best. But move. We have Mars. So right in the middle, you see this gigantic canyon. That's the Valles Marineris, or Valles Marineris, if we're speaking Latin. To give you an idea of the size of that, let's see, California to the other side. It's the size of the continental United States, but the entire planet is 1/3 the size of Earth. Now, here's the sad story. Mars probably once had life. Mars probably once had large-scale life. Unfortunately, it was killed by something. It was killed by something roughly the size of Moon, and it went plowing through it. Mars is not a very big planet, and that impact was enough to fuse the crust and more or less shut down the planet. It was not so much a killing blow, but it was a big enough hit that the planet was going to bleed out over a very long period of time. Now, it's very likely, although we have no evidence, I need to be extremely clear, that there is still microbial life on Mars. We have not seen it. There's extremely putative evidence of it, but nothing concrete. Within your lifetimes, it is very likely we will get that evidence. So Mars is possible. Mars is what we would call doable, but it's not the only place in our solar system we can have life. There's Europa, which is one of the larger moons of Jupiter. It's a giant ice ball. But underneath this surface of ice, all these cracks are in the ice. And beneath the ice is an ocean. And deep, deep, deep down inside that ocean, much like deep, deep, deep down in the oceans on Earth, there are life here, or there is life here. Tube worms and methane worms and things like this. So deep at the bottom of this thing might be life. We won't know for a long time. That's going to be a tremendous and Herculean amount of work. And Ganymede, another one of Jupiter's moons, also has potential for this. But again, we probably won't know for a long time. And lastly, there's Titan, which is Saturn's largest moon. Titan looks a lot like Venus. Of course, there's nothing like it. If you want to know what hell is, go to Venus. Venus is so hot, has rivers of molten lead running across it. Don't go there. But Titan is a little better. Titan's the only moon in the solar system with an atmosphere. If we look at this next image, you can see that usually it looks like a little yellow ball. While I'm here, I will state for the record, notice that there are 2 moons that are larger than Mercury. This is why we have a problem naming what a planet is. And our moon is the 5th largest moon in the solar system. But going back to little Titan for a minute, it has lakes and oceans and rivers of methane. Now, you don't want to go swimming in that. That's no good. But life could evolve in that. Not life like we have it here on Earth, but there's potential. And potential is good enough for me. So going back to our friend Frank Drake, we can call that number of Earth-like planets 2. So we're back to 4 billion-ish star systems where life could evolve. It's going to start getting a little harder, though. This F sub L is the fraction of those planets where life will emerge. I'm going to go out on a limb here and say that's 1. And here's the reason. When Earth first formed 4.5 billion years ago, we called this the Hadean era. The planet was constantly being bombarded by debris left from the formation of the solar system, and Hadean sounds close to hell because that's what it means. And we named it that because biology said there's not a snowball's chance in hell that life will form then. They were wrong. Basically, as soon as the planet cooled off, life just went going. Just emerged from gosh only knows what, and nothing was going to stop it. Now, how do we know some things like this? Well, I can tell you a brief story. We once got hit by something about the size of Mars, right about the same time. We survived because we're bigger. But the effect of this was we got Moon out of it. Not too bad. And without Moon, we really couldn't form life. But beyond this, we have survived impact after impact after impact on this planet. And each time we kill off the dinosaurs and the dinosaurs that came before them and dinosaurs that came before them, life comes back. The last time was 65 million years ago with what's called the KT event. We were hit by something roughly the size of New Jersey that plowed into the Yucatan Peninsula. It killed 99% of all living things on the planet. It killed 75% of all species in existence on the planet. Hey, look, you're still here. Life is incredibly resilient. It is tough to kill. So that's why I'm going to say F sub L is 1. So we have now 4 billion star systems where we have planets, they're Earth-like planets, and where life is probably going to evolve. But that life needs to be better than just life. It needs to be intelligent life. That's really getting tricky to say because we have no idea. Let's be conservative. We'll say 1 out of every 100 of these planets, intelligent life will emerge. And so that brings us down to about 4 million star systems with planets containing intelligent life. And of those, we need a planet where they're going to communicate with us. So what fraction will communicate? Well, on this planet, there are many intelligent life forms. We are, of course, dominant by a long shot. But I would again call this 1. Given a long enough period of time, it's all but inevitable that intelligent life will finally get to the point where they're going to build something like a radio telescope and start beaming stuff into space. We started doing it with Hitler in 1936, and we have not stopped since. And by the way, that's true. He's the first thing we ever sent into space. Don't worry, the signal's so degraded no one will ever see it. Not that they would really know who he was. But the trickiest part is this one here. The fraction of the lifetime of your star that intelligent civilization is out there communicating. Yikes! Now, in the 60s and 70s and 80s and parts of the 90s, this didn't look so good because we were like, yay, close to blowing ourselves up consistently. In the 1940s, for the first time, mankind acquired the ability to kill everyone. Yay! And we've never looked back since. And since then, we've gotten more creative. We went from atomic bombs to nuclear bombs to biological weapons to chemical weapons. My, aren't we versatile? And we come up with a new way to kill ourselves every other week. But we seem, for the most part, to have walked back from that precipice. And it seems like we might make it out of this kind of childish technological adolescence that we found ourselves in the last few decades. Now, we're not that much more evolved, but we're getting to the point where trade is more important than killing the other person, and that's good to a level. So if we take all of these factors in and we say maybe 1/100 millionth of the lifetime of the star, that gives us 4. 4 civilizations in the entire galaxy. They will, on average, be about 3,000 light years across. Remember, in our 1/10 billionth and 1 quintillionth scale, that's 5,000 times around the planet at that scale that you've got to go. Not good. But what if we're just slightly more optimistic? What if 1% of all civilizations that emerge survive? That they do not destroy themselves in this horrific and completely unforgivable moment of asinine stupidity. If 1% survive, there will be roughly 4 million civilizations in our galaxy. They will roughly be 27 light years apart. That means it would take Voyager about 500,000 years to get there, But that's doable, because we're going to find out why. And more so than getting there, we can communicate easily over that distance. We can find these people over this distance. And so we're really hoping that civilizations out there aren't quite as dumb as we were just a few decades ago. But more on that in a bit. So I need to start talking about the planets that we know. So at this point, we need to start talking about the Kepler mission. Now, Kepler was launched back in 2009 and has been working really hard ever since. It's staring at a tiny patch of sky up here between Cygnus the Swan and Vega, Lyra. Vega is just the biggest star in Lyra. And what it's doing is one job only: hunting planets. Remember, 1995, we went from 8 to 9. We're doing a little better. So at this point, what we have here is that we have identified 685 exoplanets at this point. These planets are located in 563 different star systems. We have over 1,200 planets that we think exist, and we just need a little bit more time to check the numbers. And those are located in about 900 other star systems. By current estimates, there should be 50 billion planets in our galaxy alone. This is looking better and better by the day. But we still need a lot more. So at this point, there are a lot of exciting breakthroughs going on. So let's check out one of them, because this was recent news. So here we have the Kepler 16b star system. It's a binary system, which means there are 2 stars. And around these 2 stars is orbiting Kepler 16b. It's a planet roughly the size of Saturn. It's about half rock and half gas. And again, it's parked in that little spot, tiny little spot of sky that we're staring at. And the way we see it is when the planet crosses in front of its home star, the brightness goes down. And Kepler is going to take note of that. And we go, aha, star. And we can work out a lot of this. Now, for me, this is awesome, because this is the first binary system we ever found. I grew up with Luke. He's my boy. And we all remember this iconic scene where Luke is looking out over these 2 suns that are setting on his home world of Tatooine. We knew that it was technically possible to have a binary system, but we didn't have proof until literally last week. When this came up in the news, I was like, yes, for this talk. Now, the planet has a period of about 270 days, just a little bit shorter than our own star, and it's orbiting around. This is not a place where any kind of life is really going to live. But that doesn't mean there couldn't be life in this star system, just not on that planet. But remember that stuff I was telling you about moons? So we all know the movie Avatar, of course. And if we look forwards to Kommen Sie Heiden, ja? We remember this movie called Avatar. This is not from Avatar. But the idea of Avatar was you have a moon that's sitting in a habitable location. Habitable here means not so hot that water boils off the planet, not so cold that water freezes, liquid water. We're sticking to what we know, not human beings, life like we know it needs. Jupiter has 64 moons. Saturn has 62. There are over 163 moons in our solar system alone. That gives a lot of chances for a moon where life could grow up and live, a chance in a solar system like this. And this star system exists. This is called Upsilon Andromedae D. Yes, we have very fun naming conventions in astronomy. It just tells me where it is and when it was found. But we need to do better than this. So let's talk about news from last year. Everyone last year exploded. I at least did when I went in my class and went, we did it! Gliese 581d. Now, Gliese 581 is a small star. Remember, our star is a dwarf. This is a very, very small dwarf. It's a small red dwarf star where we found a planet that at first we did not think was in the habitable zone, but we pushed it in with a little more information. This planet is about 5.5 times the mass of our planet. You'd be a little heavy there, but that's fine. Go on a diet. Water will likely be liquid there. We've run a lot of studies on this. The planet is capable of maintaining an atmosphere. It's capable of having liquid water. It's capable of harboring life. Capable. We have no evidence of it. Just means it could be done. This planet is 20 light years away. That is a very, very doable distance if we start beefing up our technology just a little bit, and we can easily communicate over this distance. But we can do better. There's Gliese 370b, which is just a little bit farther away, but this, as of literally a month ago, this was announced on August 25th, is our best hope for finding life in our galaxy at this point that we know of. The planet is about 3 times the mass of our planet. Gravity there is only 1.5 times what it is here. I weigh somewhere in the 150 range. That means I'd be somewhere in the 230 range on that planet. All right, I'm a little heavier, but I'll get stronger. I'll make it through. On this planet, we expect at the cloud tops the temperature to be about 77 degrees Fahrenheit, so think spring or fall in New England. And down towards the planet, expect something more like summer in Florida, but you guys all seem to survive. And so again, maybe. So we've gone from knowing about almost nothing to realizing there are tons and tons and tons of planets out there, and many of them give us a good chance at finding life. So with that in mind, let me show you a little bit about what we currently know. Here is every planet that we have found thus far. Notice how they're all kind of really close? They're closer than Mercury would be in our own solar system. It's because the stars that are around tend to be smaller. Most stars are very, very small. But we can kind of peel this out and look at it in a very intelligent way by saying, okay, which ones are hot and which ones are cold? We want to look at water. So we're looking for the bluish ones down here with temperatures like Earth, of which there are many. So we found a lot of planets. Even this giant one over here, we're not going to live there, but moons. If we look at size, again, there are several planets that are going to be Earth-sized. So there are a lot of good candidates out there. And we've only just begun to scratch the surface. Now, I want to really impress upon you what I mean by scratching the surface. In the field of physics, we're like 99% of the way there. Everything that we're kind of learning now is minutia. We're tying up the loose ends for the most part. In astrophysics, that is not true. We have a lot of work to go. Again, big universe. So I want to show you this. This is a little slideshow that shows us from 1980 to 2011 all the known objects in the inner solar system. So of course we have Mercury, Venus, Earth, and Mars on the inside, and Jupiter is lingering around down here. You'll see that we barely knew about anything over here. These are called the Greeks. They follow Jupiter. And see those guys over there who are just popping up? They're called the Trojans. We didn't quite know a lot about them. But each time you see a little flash, we found something. I want you to try and memorize for a moment how sparse this is. And we're just ticking off time over here. And what you're going to see is that usually we're finding things very close to Earth. So Earth is in here. Let me just use my pointer, it'll be easier. Where are you? There you are. So you'll see that wherever we are, you kind of find things close to us, because we need to be really close to you to see these things. So right about now, we should be entering into the 1990s. As we're doing so, we're ushering in a new wave of technology. And we're going to start finding more and more things. We've only just begun. As 1993 rolls around, we're going to launch Hubble. And that is going to start telling us a lot more data. Notice that the light-ups are going to start getting bigger and bigger as we're figuring out how much stuff is actually in our solar system. We're still in the mid-90s, 16 years to go. And by the way, this is how we're finding out what might one day kill us. Remember, 65 million years ago, something hit. We expect to get hit every 75 million years or such. We're coming up due any old time now. So, you know, say hi to Mom. Hey, look, we're finding lots of stuff. And you're going to see us finding more and more and more. Now, mind you, this video has now ticked off 20 years. This is our neighborhood. This is like looking around your yard and saying, oh, I didn't see that thing there before. When we're looking for planets, it's like trying to look across the state of Florida and going, oh, I think I see something. It's not easy. if you try and look at Uranus in the night sky, and if it's dark enough, you can see it. It's about the size of a golf ball, a kilometer away. So yeah, it's actually getting so dense my computer's freaking out over the density in trying to parse this much information. But you can see that the discovery rate is becoming explosive. There are so many things in our solar system, and again, scratching the surface. This is home. I cannot impress upon you how close to us this is. This is the asteroid belt. This is 3 times farther away than the sun than we are. This is closer than Jupiter and the rest of the solar system. There is a lot out there yet for us to discover in our own solar system, let alone in our own galaxy, let alone in the universe. Remember when I said 400 billion stars in our galaxy? Yeah, there are like 100 billion galaxies out there. You got to see a bunch of them. So that's what we know at this point. So let me kill you. Good. Now I'm going to finish up by talking for the last few minutes about the Drake equation, because that's what, not the Drake equation, the Fermi Paradox. Because that's what people always want to hear. So in the 1950s, Enrico Fermi, Italian-born American physicist, Nobel laureate, helped build the bomb, and a bunch of those other guys who helped build the bomb are sitting around a lunch table in Los Alamos, New Mexico. Why are you there? And Mel. Good. And they're talking about all the stuff I've been talking to you about tonight, and they're giving the same kind of arguments. The arguments have become slightly more sophisticated as time has gone on. But Enrico asked this simple question, and he disarmed and shut up everyone at the table. He said, well, if there are that many alien civilizations in the galaxy, where are they? Why haven't we met them yet? Why aren't they here to say hi? That's a tough question. 60 years later, we don't have an answer. We have speculation. So let me give you a few of the answers we know so far that aren't answers. 1, we're first. Go us. Earth formed at the peak of planetary formation in this galaxy. So it's incredibly possible that we were the first out of the gate. And the reason we haven't met anyone else yet is because they're all technologically behind us. Now, mind you, first flight in an airplane, 1906, Kitty Hawk. 63 years later, we land on the moon. Within almost half a century, we went from a flight that lasted less than 20 seconds to landing on something 400,000 kilometers away and then coming back. And then we did it several more times. It's also possible that it's in the nature of intelligent life to destroy itself. We discussed this earlier. We've certainly flirted with this considerably. It's entirely possible that all intelligent civilizations basically just blow themselves up. Darn. It's also possible that the universe, it's not possible, it is true. The universe is an incredibly dangerous place. We've been whacked many times. The first billion years of existence in the solar system is called the heavy bombardment. Well named. Everything was getting blown up. But even since then, we've kept getting blown up, and that's nothing. There are things called magnetars, and these are one of my favorite ways to die. Back in the 1970s, a magnetar about a quarter of the way closer to the center of the galaxy, so that's about 3,000 light years away, burped, basically. And this burp fried 3 Department of Defense satellites and destroyed about 17 Soviet satellites. That was a minor burp. That was like a hiccup. One that was slightly closer, 500 light years away, back in 2004, and I kid you not, nearly blew the atmosphere off of our planet. Needless to say, if that had happened, you would be dead. Like that. And by the way, we have no way of detecting them. We have no way of stopping them. This isn't like Armageddon, some big asteroid coming at us, and we figure out some way to get rid of this problem. Not going to happen. We don't have anything capable of anything like that. So I'm not going to talk much more about doomsday scenarios because there's going to be another lecture coming up by my colleague, Dr. Kevin Mackay, who's actually going to talk about Armageddon scenarios later on. Yes, it's a plug. We want you to come back. It's also possible that it's really hard to travel between the stars. How hard is it? Good question. Well, let's build a moderately sized spaceship and try and move it up towards the speed of light. We'll ignore relativity because it gets complicated at this point. But the amount of energy it would require is about 1% of the energy that the sun gives off in a second. That doesn't sound so bad. That's more energy than mankind has produced and used in our entire history. It's more power and energy than we will likely create and use in the next 1,000 years. Yeah, that's going to be challenging. So it's incredibly possible that moving between the stars is not very feasible at all. And so interstellar travels us out of it. You're never going to meet anyone. We might talk to them. Sending radio waves is cheap and free and easy, but sending them a spaceship, not so much. Lastly, there's the one that we all kind of grew up with, which is called, uniquely, the zoo hypothesis. Basically, it goes like this. They know we're here, and they either don't want to talk to us, they don't like us, or they think that we are so dumb that we just aren't even worth wasting the time on. Because they go, oh, aren't you cute? And you're on the planet still. That's so nice. And they basically look at it saying, well, we could roll over them at any time we want. Or we could say, well, if we share with them our technology, look, they're almost killing each other already. They spent half of the last century basically threatening to kill each other. Let me be clear. We have the technology to split this planet clean in half if we wanted to. Please don't. I need research funds to keep going. That would seriously dampen my day. But the idea of this is, in Star Trek they call this the prime directive. Don't screw with aboriginal cultures who are just getting warmed up. And if you can travel between the stars, we are like the dumbest people you have ever met. We really have nothing special. The only other good answer I know of is that there could be one dominant culture. And this dominant culture goes out into interstellar space, and anytime there's a competitor, they go, bye. I don't buy this. And the rationale is very simple. War is always fought over one thing, resources of one kind or another. Go back to that galaxy is a big place, the universe is a big place. Anything we have here on Earth, you can get anywhere else in the solar system. Every time I see an alien invasion movie come out of Hollywood, I go, you idiots. I always tell my classes this. Look, you have two fields you can plant your crops in. One of them is empty and one of them has wolves. You have a great big gun, and you are not terribly scared of wolves, but what if they happen to bite you? Just a little bit. Why risk it? Plant where there are no wolves, even though you can kill them all. You want water? Go to Mars. Go to Ganymede, Europa, Callisto, Io, Titan, Neptune, Uranus, Jupiter, Saturn. They all have water on them. And lots of it. The only thing that's unique about this planet is us, and I assure you they do not want us. We are not really good at anything at this point. So we are just beginning to wander down this road. We've come a long way from my beginning of looking up at the skies, and all the people who've come before me who have sat around thinking the exact same thing, trying to figure out our place in the universe. We've come a long way. We know where we live. We know a lot of stuff. But we do not yet know if we're alone. I say if we are, that's a real crying shame. And statistically, whew, I'm going to buy a Powerball ticket tonight. Thank you.
Facebook.com/USF Physics Lectures. Remember, that's where we're going to put every bit of information how to do these lectures. Also, if you have questions that you don't think of now and you want to ask Dr. Gobeille later on, you post them on there and he'll get back to you directly. Any questions for Dr. Gobeille? Please fire away.
Yes, sir.
How long did it come up with awesome and engaging speech, actually? I'm curious about that because I kind of walk into most things a little skeptical about whether or not I'm going to be interested because I'm ADD as all hell. And you managed to do a very good job.
Well, thank you. The question there was how long did it take me to come up with the idea about, oh, I don't know, a second. But the actual speech takes about an order of a day. I probably put about 10 hours in this. But in fairness, I've taught 3 full-blown courses on the search for life in the universe. I've spent the majority of my life on this planet thinking about this topic. So in fairness, I might say decades. And that's a bit more legitimate of an answer than a day. So somewhere between a day and 25 years or so.
Somewhere in that.
It's plus or minus something. Yes, ma'am.
Planets that, like the system you were mentioning, the Gobeille system, when they find planets that they're large like that, like 5 times the size of Earth, obviously the gravity is too great, theoretically.
Possibly.
Are they only looking at the moons or the possibility of moons, or do they really think that there might be intelligent life on a planet that large with that kind of gravity?
That's a great question. So the question comes down to size of planets. Now, there are 2 things that come into gravity. Yay, physics time. So we all know and, of course, love Newton's law of universal gravitation, which says, all right, take the mass of the planet and the mass of the person standing on the planet, and it depends on the radius of the planet. So there are 2 things involved, the mass of the planet and how big the planet is. Well, it could be 5 times more massive, but what if it's a lot smaller? Or it's going to be a lot larger in this case. They can balance out. So gravity is oftentimes a tricky thing to work out. I need to know the mass of the planet. I can do that most of the time to a good error. Size I can also do, but that's still tricky. As for moons, we know of no moons at this point. They are just literally too small. When you have that little light curve that I showed earlier on, so something moves in front of the star. If a moon moved in front of it, nothing would happen, pretty much. But when a planet moves in front of it, you're going to get a little dip. At this point, I would actually make a plug and say there's a site called Planet Hunters. I can't remember if it's .org. It probably is. Just go on Google. You can help out in this search. And they are actively pursuing civilian scientists, people who know nothing about science. You don't need to know anything at all to go and help out. There's so much data. It's impossible for the limited number of researchers to parse through this data. So if this stuff is interesting to you, you can legitimately help. 2 civilians were the ones who actually found Gliese 370b, which is the best chance that we have right now.
So there's no wobble on planets when the moon's orbiting on stars?
So yeah, there are a few ways that you can really find planets. If you go to a really big planet, what happens is your star moves back and forth, right? And so we can see this if I look to, gimme. Yep. All right, here is a diagram of where our sun has been for the last 50 or 60 years. And I know I should have kept this out. You can see that sun wobbles around a lot. And it's basically where Jupiter is. So you can watch a star wobble. That tells you something big is moving around it. You can look at the light curve, like we've looked at here. And there are other processes, but they get a little sketchy. Most planets we know about are one of the 2 methods I just told you about. But again, moons aren't really going to make anything move. They're just too small, unfortunately. I mean, these small Earth planets are also incredibly difficult to detect. Really, really hard. That's why finding an Earth-sized planet is just really difficult right now. We're getting better. We're building better observatories. We're building better techniques. But again, scratching the surface.
Will you guys be using the Webb telescope in the launch? You really want to, but
the Jim. No. That is politics. I feel like Mel Brooks. The Jim Webb telescope, when I was a high schooler, was supposed to come out in 2003. When I was in college, it was supposed to come out in 2008. A few years ago, it was supposed to come out in 2013. And 2 months ago, it was supposed to come out in 2016. And as of today, it's supposed to come out in 2018. You can see now why I'm kind of... It's $9 billion over budget. It is the biggest elephant in the room at NASA's budget, and it's consuming about half of it. And there's another project which consumes the other half, pretty much. And there's this pittance left for other projects. Jim Webb will likely not do a lot of this work, a little bit. Jim Webb is going to be used more to look at those extremely distant galaxies. It's not an optical telescope like Hubble. It's going to be an infrared telescope that sees a bit of optical. And so remember where all those galaxies got red at the beginning? That's why we're looking at infrared. That's where everything's going to be. But yes, there's a potential for it, and if we see a really good candidate, we'll point at it, because Web's going to be significantly more powerful than Hubble currently is. But right now, Hubble's likely going to end before Webb goes up, much like the space shuttles ended before we kind of fixed that problem.
One more quick question. I don't want to hog.
Sure.
Is there any possibility that you or one of your colleagues could come back and talk about spatial expansion and like the background theory and stuff?
Ah, cosmology. Hey, Rob, how were those talks in the class last week about cosmology? So, yeah, I'm always thrilled to talk about cosmology. Space is expanding, nothing, boom, everything, and a lot of in between. So, yeah, I mean, absolutely, if SPS invites me back, if I haven't embarrassed them sufficiently tonight, then yes, I would love to talk about cosmology. Yes, sir.
Since we already have the technology to travel out to space, land on the moon and back, why haven't anyone been to Mars?
Politics, 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 politics. I can give you a few good reasons. One, expense. Basically, the space race was a game of one-upsmanship between the Soviet Union and the United States. It was basically like, we're better than you. No, we're better than you. We're better than you. And that worked for astronomy, because we were like, yes, keep giving us money to say we're better. That worked very well. But we won, they quit, and everything kind of went downhill from there. The interest hasn't been there, and I've argued for years that I was born in the wrong era. If I had been alive in 1969, I would have been like this to my TV. I probably would have gone blind watching, Apollo 11 going up. I think it's very important that we go back, but again, there are challenges. It's cheaper, faster, easier to send a small robot. And so in August of next year, we're going to be sending, not Phoenix. I can't remember. Mars Science Laboratory. I can't remember its colloquial name, but it's called Mars Science Laboratory. Richard, do you remember what it's called? I'll get back to you on it. It takes a lot. Our speed record for going to Mars right now is about 2.5 months, and that's not bad. You need food and water for 2.5 months too. Land. Stick around for a while. If I'm sending you a 2.5-month trip, you're staying, whether you like it or not. And then 2.5 months back. This is a lot of stuff, and that requires a lot of energy to get there. With the space shuttle, 9 pounds of every 10 pounds that you were bringing up was fuel. So for 1 pound of you, I need 9 pounds of fuel. Mars will likely kill you. The atmosphere on Mars is, of course, not breathable, but the sand and the dirt is this very silicate material. One of our astronauts breathed in moon dust, and that almost killed him. It was like inhaling fiberglass. And that's very, very challenging. I would note that if I sent you with a shovel and gave you a week on Mars, you would tell me more than I already know about the planet from all of the effort we've already put in. Because robots cannot do what a human being can do. When Spirit, one of the twin rovers that we launched to Mars, started kind of like limping its leg behind it and dragging a little ditch and digging a little ditch behind it, that's when, great, a shovel! And they turned and they looked. They went, aha, we can see into the soil, and it was this great big thing. NASA's pretty good at turning a bad thing into a good thing. Except when we plow things into Mars. The other plan that I'm actually a really big proponent of is called the geriatric plan, which is, or the terminal plan, which is to take someone who's either elderly or sick or dying. Young and dying is probably better because you'll be able to survive a little bit longer. One-way trip. You're not coming back. We're sending you there to die. But I assure you. This, I'm not kidding though, this is a plan fielded by NASA, and if I was told you have 3 years to live, I'd be like, shoot me out there, baby. You'll get me there, you'll find me 20 years later when we land, like, just, that sounds like one hell of a way to go to me. Difficulty.
We've got time for one more question. I don't want to keep everybody here all night, but I'm sure Dr. Gobeille will be willing to hang around.
Sure.
One more question?
Billy?
What would you say is currently our most successful way of detecting Earth-like planets? I know there are 4 ways they've been detecting them in the past. Which one do you think stands the best chance of netting us the most Earth-like?
Transit, probably. I mean, you just need a photodetector that is sensitive enough. Transit's the method that Kepler uses. Again, we watch the light curve. Because if I'm literally looking for Earth around any star, Earth is not going to give me an astrometric wobble. It of course does, but it's going to be very, very small. If I'm looking for like gravitational lensing, way, way too small. Yeah, transit is definitely going to be your best bet, because I think we'll be able to make a sensitive photodetector long before we would make a telescope powerful enough to do that. But I have an exception, a technique that doesn't yet exist but will shortly. Plug time. I am a radio astrophysicist. I love my job because Hubble is a very small telescope. Those telescopes you saw at the beginning of the talk, those are several meters across. My telescope is 36 kilometers across, and that's a small radio telescope. I can make a telescope the size of the planet. Oops, we already have. I can make a telescope bigger than the planet. Oh, we already did that too. Radio astronomers are capable of a technique called aperture synthesis, which is not yet feasible in other wavelengths. Radio waves are anywhere from millimeters, I can measure this with my hand, to meters and meters and meters across. But when we talk about light, I can't show it to you. Nanometers across, tiny, itty bitty, billionth of a meter. I need to know to the precision of one wavelength, to a precision of 1 billionth of a wavelength, where the distance between two telescopes are. And the problem with this is we've done this with some telescopes, but they're very, very close. You need to be able to make them very, very far apart. And there are these things called plate tectonics that move constantly. In fact, when you do aperture synthesis, what I do, we get money from geological surveys because they can reverse engineer our data to do what's called geodesy, where they track the motion of the plate tectonics using data from radio astronomers. We give better and more accurate data than anyone else. Infrared telescopes are starting to do this. And if I can make a reasonably sized interferometer out of infrared telescopes, well, guess what? It's a warm planet here. We give off heat. It's possible that I can make a big enough infrared interferometer within the next 30 or 40 years. We've already started building them, where I could see literally an Earth-like planet orbiting, not watching its light dip, not watching a star go, but watching the planet move around the star if it was in a favorable orientation to us. That's going to be how we're going to do it.
Folks, let's thank Dr. Gobeille and SPS folks that made all this possible. I don't know about you, but talks like this always make me hungry. And SPS folks are trying to raise money to sponsor more talks like this, and you can help by spending $1 and buying some refreshments on your way out the door. If you'd like to hang around and talk with Dr. Gobeille, please feel free. If you want to ever contact anybody with SPS or in physics, physics.usf.edu, we're all in the directory. You can send anybody an email and they'll get it to us. Thank you for coming out this evening.
Take it easy, buddy. I just want to put up. Thanks, man.
Great presentation.
Thank you. Thank you very much.
I just had a question.
Sure.
By the way, good presentation.
Give me 1 second because I just want to attempt.